Everyone. Yeah. 1, 2, 3, 1, 2, 3 testing. Good morning, everyone. Good to see you for the second day of our lectures. I hope everyone's had a restful night. Some of you just arrived. Others already had drinks and got together last night. That's great. Off we start. People on Zoom can hopefully hear us. People on live stream can see us. A couple of things. I see these kayaking sheets are still there. What are they called? Waivers. Thank you. Print your name, please. I see people scribble their signatures. Print your name on top of each one. Maybe come back if you haven't done so. Any other concerns or questions? I can't think of any. Okay, we can get started. We have first lecture or a couple of them by Frank again on Galaxy Halo connection.
All right. Good morning, everyone. So let's continue where we left off yesterday. So today we're going to talk about empirical constraints on the Galaxy Halo connection, and we're going to slowly move into cosmological constraints, and then we're going to break it down into what the outstanding issues are. So just to recap quickly what we talked about yesterday, I basically told you and showed you that we have an analytical formalism by which we can compute for any cosmology a halo mass function. Tells you how many halos of a given mass do I have per co-moving volume. We have seen from simulations that dark matter halos, when they realize, they form NFW profiles, okay, a universal density profile, and it's characterized by a concentration parameter. And we can compute for a given halo mass and a given cosmology and a given redshift what that concentration parameter is. We have models for that as well. We understand how to model that, and that's to do with the assembly history of the halos. Remember, more massive halos assemble later and are less concentrated. We also learned about the fact that dark matter halos themselves are biased traces of the dark matter mass distribution, something we express in terms of the halo bias function. And again, we can compute this analytically. We can compute how the bias depends on halo mass. And what we learned there is that more massive halos are more strongly clustered. And finally, we can calculate the linear matter power spectrum, P linear, okay, with the initial power spectrum multiplied by the transfer function squared, okay, which you can compute with CAMP, for example, and then multiplied by the linear growth rate, D of T, okay, which you can also compute analytically for a given cosmology. And those four ingredients combined, together with what is called the halo model, now allows you to compute analytically the nonlinear matter power spectrum. Okay. You can combine that with a halo occupation model that describes in a statistical sense how many galaxies are there in a given halo and what their properties are. Okay. You can either use an HOD, which specifies in a given halo how many galaxies are there on average above a given luminosity threshold. Or you can use a conditional luminosity function that says at a given halo mass, how many galaxies are there on average of a given luminosity. You combine either of those two things with the halo model, and now you can compute the galaxy-galaxy two-point correlation function for any luminosity range you want. And that's an observable. And the best thing, you don't need any explanations. This is analytical. During the time that you guys were downloading Garrison's Halo catalog yesterday, you could have used this to compute 100 powers per correlation function for galaxies for different topologies. It's wickedly fast. Okay, so that's the power of this formalism. So now we're going to see what we can learn in terms of constraints from clustering. All right. So once again, another quick recap. We have this analytical blah, blah, blah. It's small, you don't need to learn it by heart. Okay. For a given cosmology, we can calculate the halo mass function, halo bias function. Pictorially, what it means is we know what that looks like. There's a bunch of halos. We know how many, how they're distributed in space. We can compute a halo-halo correlation function. You guys have known how to do that now. But in Python, you know. You combine it with a halo occupation model. That halo occupation model basically describes how many galaxies there are in all of these things. And you can combine it and you compute the galaxy-galaxy correlation function. And I've shown you how from these two things, you can compute the luminosity function. Those are observables. Okay? We have data on those things. Your model is basically the halo occupation model, which has, say, if you take the luminosity function, the conditional luminosity function, about 10 free parameters. For each choice of the 10 free parameters, you can very quickly compute these and compare them to the data. You put this in a Bayesian engine, MCMC, whatever, and you can put constraints on those parameters of your model. And then you can try to change cosmology, which changes these things, and you can do it again. And maybe you can learn something about cosmology then. That's the idea. Just to show that this really works, here is from a paper in 2013 that I wrote. What I did is I take an embodied simulation, I find the dark matter halos, and I make an assumption about my conditional luminosity function. I pick values for all my 10 free parameters. It means I've specified the halo occupation statistic. For each halo now, I draw, according to that conditional luminosity function, I draw luminosities for the galaxies that live in that halo, and I put them in the halo. And then I compute the correlation function for galaxies in that simulation box. That is what you see here in the circles for different magnitude bins. And then I say, you can also compute this analytically using this entire framework, and those are the solid lines. And you can see this analytical model is in perfect agreement with the simulation results. So you really don't need the simulation. You can see it's really accurate, a few % accuracy. You can even break it down into one halo, into two halo terms, etc. Not that important. Okay. But the point being, yes, this is as accurate as the simulations, and it's much, much faster. Okay. So that's just a proof of concept. Now let's apply it to data. So this goes back 2004. My collaborators and I wrote one of the first papers where we actually tried to do this, applying it to data. Back then, there was no Sloan Digital Sky Survey yet. Okay. What we used was a 2-degree field galaxy redshift survey. So here's a luminosity function. Okay. And here are plotted the correlation lengths as function of magnitude. Now, the correlation length is just a single measure that quantifies the clustering strength. It's defined as the radius at which the correlation function is unity. So just all you have to remember is it's a measure of clustering strength. So larger correlation length means more strongly clustered. And what you see in the data, okay, the blue dots, you see if you go to brighter galaxies, for the real cosmologists here, okay, magnitudes, this is bright, this is faint. Right? Brighter galaxies are more strongly clustered. Remember, I told you, more massive halos are more strongly clustered. So apparently brighter galaxies live in more massive halos, and it makes sense. Right? So the yellow, or whatever that color is, contours are the 68 and 95% confidence intervals from fitting to this data. And this just shows, okay, we can fit the data nicely, okay? And this means fitting the parameters of my conditional luminosity function. And then here are the posterior results. So I'm now plotting the inferred average luminosity of central galaxies as a function of halo mass. Okay? And what you see is sort of this broken power law relation. Okay? So apparently there's a broken power law relation between the luminosity of a central galaxy and the mass of the halo. Okay? So this was one of the first results that used clustering data to constrain this galaxy halo connection. Fast forward a few years, Edith Zahavi's work in 2011, taking the correlation functions as a projected correlation function. Don't want to go into the details. It basically means you project it along the line of sight. That way you get rid of what are called redshift space distortions, for those of you who know what those are. So projected correlation function is function of projected separation for 9 different luminosity threshold samples. All galaxies brighter than -22, all galaxies brighter than -21, etc., etc. Okay, the data points are the data. The lines are Edith Zahavi's best fit model, which is based on an HOD model. Okay, so for each of these 9 bins, she has 5 free parameters, fits it to the data, and then here are the results of those best fits results in terms of how many galaxies are there of that luminosity in a halo of this mass. And you sort of see this characteristic transition from 0 to 1, and then at some point the satellites kick in. Okay. So this is sort of how you can indeed constrain these galaxy halo connection. Now, around the same time, some other people realize that there's another way you can do this. And that's become known as sub-halo abundance matching. Okay. Remember that I told you yesterday the key premises of all this stuff is that galaxies form and reside in dark matter halos, and that there is some property that is tightly correlated, galaxy property that's correlated with the halo property. Okay. And sort of what we have seen, that what we infer is that the luminosity seems to be nicely correlated with the halo mass, albeit by a broken power law, but there seems to be a nice correlation there. Now, when people realize this, you have to tell, okay, that was for the central galaxies. Okay, the central galaxy is nicely correlated with the mass of the halo. But what about the satellite galaxies? Are their luminosities tightly correlated with the mass of the subhalo? Well, not really. And the reason is the following. If you look at the satellite subhalo, a subhalo, its mass evolution function of time. Basically, what happens is it starts growing, it forms a halo, and then the halo grows. And this is the time when that halo is still its own host halo, before it falls into a bigger halo. So it's just accreting in mass, just like a normal halo. And at some point here, it is accreted into a host halo. It now transitions from being a host halo to a subhalo. At that moment, it starts to be affected by tidal forces from the host halo that strip mass away from it. So its mass is going to plummet like this, okay, due to tidal stripping. Okay. So the present day mass of a subhalo is here, but at some earlier time it was much more massive, at the time of infall, at the time of accretion. Now, we think that the galaxy sort of was following along here, was also growing. Whenever the halo grows, probably there's new star formation going on and the stellar mass grows. But then when it falls into the halo, we actually think that probably the galaxy quenches. And that's because it becomes much more difficult for that galaxy now to acquire new gas coming in, because that gas is stripped away. There's ram pressure stripping operating. So people believe that shortly after a galaxy falls in, it's probably going to be quenched. It means the star formation goes to zero. What about the stars? Are they stripped? Well, ultimately, perhaps yes, but initially, that central galaxy sits at the center of the halo. The stripping operates from the outside in, so you can strip a lot of dark matter and not affect the stellar mass of the galaxy. So probably what happens is the stellar mass grows, but then the stellar mass sort of stays fixed here. It doesn't grow anymore because quenching of star formation. And it doesn't go down significantly because all the stripping mainly removes dark matter mass. So people said, okay, so maybe then the luminosity of a satellite galaxy is not correlated with the mass of the present day subhalo, but of the mass of the subhalo at accretion, M accretion. Okay? And if you make that assumption, okay, it basically is motivated by this idea about selective quenching, what you can do is you can do a very simple thing. Okay? And that's abundance matching. So you go to your halo catalog, dark matter only simulations, you find all the dark matter halos, okay? And then you look at the subhalos. But for the subhalos, what I'm plotting here is not the present day mass of the halo, but the mass of the subhalo at accretion. And now you get a total mass function of all halos and subhalos. Okay? Again, for the subhalos, it's crucial that you use a mass at accretion. And now you go to your galaxies, your observations, and you plot the cumulative number density of galaxies function of luminosity. Okay, so the luminosity function. And now what you do is the following. You say, pick a given halo mass, read off what is the abundance, how many halos are there more massive than that, go over to the galaxies and read off at that abundance, what is the luminosity. And now you say, I'm going to assume that halos of this mass contain galaxies of that luminosity. You're basically matching the abundances of those objects. It's another way of making a galaxy halo connection. You're just assuming that it's a perfect rank order correlation between the mass of a halo and the stellar mass or the luminosity of a galaxy. Does that work? Amazingly, it works amazingly well. Okay, this was from a paper back in 2006 by Charlie Conroy, and the red dots are Sloan data. And what they did is they took a numerical simulation, abundance match galaxies to those halos and the subhalos in that simulation, and then just go in the simulation and ask, what is the correlation function of these galaxies now? And compare it to the data, and that's the blue line. And it fits. And this model has 0 free parameters. You just abundance match, done. No MCMC chain to run to find the best fit model parameters. And then you can plot the number of galaxies that you have in this system's function of halo mass, and it looks like a typical HUD model. So this is another way in which you can do this. This supple abundance matching seems to work. Now I said there's 0 free parameters. Well, one thing that it implies, if this works so well, it really suggests that indeed that idea is correct, that galaxies basically quench their star formation roughly when they fall in. And there's a whole literature on quenching if you're interested in that stuff. I told you there's 0 free parameters, but at some point people realize, well, you can actually wiggle around a little bit, because you can decide what property of the halo am I going to use when I do the abundance matching? I told you can use the mass at accretion, but maybe you want to use the maximum circular velocity of the halo, and people have used that. So Vmax, the maximum circular velocity at the moment of accretion, okay? Or M peak, which is the maximum mass that the halo ever reach in its life, which is typically very similar to M accretion, but often a little bit larger. So you can make a choice of which halo property am I going to use. And if you do that for different halo properties and you make predictions for the clustering, you see it makes small changes. So you have a little bit of freedom there. You can also decide when I do that rank order matching, I'm not going to assume that the rank orders match perfectly. I'm going to assume there's some scatter in the rank order matching. Okay. You can add some scatter to that matching. And that's also a free parameter. You can make that scatter larger or smaller. And again, that changes the clustering strength. So people have played around with this quite a bit. There's a very nice paper by Radic et al. Show how your fit to the data changes and depends on all these parameter choices. So simple abundance matching is in principle very powerful, but it has a few downsides. First of all, it basically only works on complete samples of galaxies, because you take all the halos in your simulation and then you're going to rank order match them to galaxies. It's better match it to all galaxies, because if you only would pick blue galaxies, then you have no reason to believe that this would work. In fact, it won't work. So it only works for complete samples of galaxies. Secondly, you need a goddamn simulation. I've been telling you here that it would be nice to get rid of these simulations. We can do this analytically. Now this method needs simulations. Okay, some people like that. Or here's another problem. I told you yesterday at the end there is this artificial disruption issue. The subhalos in the simulation do not have the radial profile of satellite galaxies. And we typically need to add orphans to it. And that means typically in subpolar abundance matching, you need to have some extra stuff that you need to it. Okay? You need to model these orphans. And there's some degrees of freedom there that people have started to incorporate. Anyway, it nevertheless is an extremely powerful method, and we'll come back to it later today. So that's galaxy clustering. You can use the clustering to constrain the galaxy halo connection. But there's other ways in which we can do this, other kinds of data. And one way you can do this is galaxy-galaxy lensing. So what is galaxy-galaxy lensing? I'm sure that Gary Bernstein is going to talk about this in much greater detail. Pictorially, what galaxy-galaxy lensing is the following. Suppose you have a bunch of background galaxies, high redshifts, whatever. And now you take a foreground galaxy with its halo and you put it in front of it. What is going to happen is you're going to create what are called tangential shear distortions in the background galaxies. Now here, I've highly exaggerated that for pictorial reasons. In reality, this is a really, really small effect. Okay? But observers are really, really good at measuring things. And if you do this for enough galaxies, you can pull out a signal. You can't do this for an individual galaxy. But if you stack the signal for many, many, many galaxies of a given luminosity, you can pull out this signal. This shear distortions, this tangential shear distortions, is typically turned into something called the excess surface density, delta sigma, okay, which is just basically just a measure for this strength of this gravitational lensing. And the strength of this gravitational lensing, of course, depends on mass. It's directly probing the mass of that halo here, which is doing the deflection of the light. Okay. So you can actually show that its excess surface density ultimately depends on the galaxy dark matter cross correlation. It's a cross correlation between this galaxy and the mass associated with it, because that is doing the lensing. Now, I told you how with this halo model framework, I can compute the dark matter correlation function. I told you how I can compute the galaxy-galaxy correlation function. With the same formalism, just changing one line in your code, you can compute the galaxy dark matter cross correlation. It's trivial. I hope you can see that. That means once I make an assumption for my halo occupation model, like the CLF, I can use the same framework to actually make a prediction for what this signal should be. And I can compare it to the data. So here is the data. This is really wonderful work by Rachel Mandelbaum in 2006, based on Sloan data. And what she did is she went to a bunch of magnitude bins. So she picks all galaxies that are in the range from -18 to -19 in magnitudes. Okay, so about 30,000 galaxies. And around all those 30,000 galaxies, she measures all the shapes of all the background galaxies. And out of that signal, she pulls out the excess surface density. And then she does that in different magnitude bins. Okay? You can see how many galaxies are stacked together here, like 140,000 galaxies, but you have a wonderful signal. And what you see is that if you go to more massive, more luminous galaxies, you see that the lensing signal gets stronger, indicating that these more luminous galaxies apparently live in more massive halos that are causing larger shear distortions. So you see by eye, once again, brighter galaxies live in more massive halos. Now, I told you that you can model this, but there's one thing you have to really keep in mind here, and it has to do with the stacking. As I said, you can't take an individual galaxy and get a signal. It's too weak. You have to stack galaxies. So suppose this is what the universe looks like, pink halos, for crying out loud. But suppose that the galaxies that you stack that have a given luminosity are the blue ones. In low mass halos, these blue ones are central galaxies, but they can also be satellite galaxies in much bigger halos. And now I stack all of them together, basically like this, and this is what I've measured with my lensing signal, this mass distribution. It's kind of a mess, right? This looks like a disaster. How are you going to model this? Well, you have all the ingredients. In order to model this, all you need to know is what is the probability for central galaxies of that luminosity to have a given halo mass? What about the satellites? What fraction of these galaxies are satellites, and how are the satellites distributed in your halo? Those are exactly the same ingredients that you need to compute the galaxy-galaxy clustering. So with exactly the same formalism, I can compute this lensing signal and compare it in a meaningful way to the data. So here it is. Here is an actual fit to this data. The same data I showed you before from Rachel Mandelbaum. This is Marcello Cacciato's work in 2009. And the solid line is sort of the best fit to the data. And you can see how you can break it down in all the different terms, the one halo, the two halos, central satellites, what fraction contributes. Okay. And you can see you got to get a good fit. So here's another method that you can use to constrain the galaxy halo connection. And people are using it abundantly. And we'll come back to that in a bit. There's a third method, fourth method. Where are we? I lost count. Satellite kinematics. There's another way to do this. What is satellite kinematics? Satellite kinematics is very simple. You have a halo, you have a central galaxy there, and then you have these satellite galaxies that are zooming around. The faster they move, the deeper the potential well, the more massive the halo of the central. So you can gauge the mass of the halo of this central galaxy by probing the velocities of the satellite galaxies. And if you use the virial theorem, which I hope you'll remember from grad school, from undergrad school, you'll learn that the mass is proportional to the velocity dispersion times the characteristic radius, okay, how far the satellite's away from the center, divided by the gravitational constant. So you have to measure the velocity dispersion of the satellite galaxies, and you have a measure for the mass of the halo. This method is very old. This method goes back to a very, very famous paper by Fritz Zwicky in 1933, when he applied this to the Coma cluster. He measured the velocities of the Coma cluster galaxies. He inferred a very large velocity dispersion. He inferred a very large mass. And he realized that that mass was about 400 times higher than the mass he got when he just added up the masses of the galaxies. And so Fritz Zwicky concluded, for those of you who speak German, that dunkle materie must be present, dark matter. This was the first mention of dark matter. This was basically the first detection of dark matter back in 1933, okay, based on satellite kinematics. So typically nowadays we do it a little bit more sophisticated. We don't use the virial theorem, we use the spherical Jeans equation, which you also hopefully remember. It's basically the same thing, right? Except that you have some corrections here. So you have a radial profile of the satellites in the halo. You have the radial profile of the velocity dispersion. And then you have this nasty thing here, beta, which is an anisotropy parameter. Okay. Typically, we assume that these things are isotropic, but that's not necessarily true. And if the anisotropy is different, then it can affect your mass estimate. It's called the mass anisotropy degeneracy. There's a way to break it, though. But typically, people assume isotropy. Okay. But anyway, these are just technical details. How does this work in practice? Because if you just go and you look at a bunch of galaxies on the sky, they're not labeled by I'm a central and I'm a satellite and I belong to that central, unfortunately. So you have to somehow find out which ones are the centrals and which ones are the satellites. And the way you sort of do this is by putting isolation criteria around galaxies. So you go to a galaxy Okay, galaxy, you put a cylinder around it of a certain radius and a certain depth. Okay, and you say, if I am the brightest galaxy in my cylinder, then I consider myself a primary, and this probably means I think I'm going to be a central. Okay, so let's assume that those are centrals, because typically the brightest galaxies in the halo are the central galaxies, right? Think of the Milky Way. The Milky Way is a hell of a lot brighter than the LMC or the SMC. Then you go and you place a second cylinder around it, and you say all the galaxies that are fainter than that galaxy in that second cylinder I'm going to call secondaries, and I'm going to assume that they are satellite galaxies in the halo of my primary. Okay. And you can just tune these sort of cylinders, the depth of the cylinder and the opening angle of the cylinder by just, testing this on mock data sets and, optimizing it for impurities and that sort of stuff. What you then get in the end is a list of primaries and the corresponding secondaries. And for each primary secondary pair, measure from the spectra the line of sight velocity difference, delta V. And then you plot that delta V as function of the luminosity of the primary or the central. And here you see actual data from Sloan, and you see this sort of trumpet shape. What you're seeing here is that if you go to brighter galaxies, you see that the velocity dispersion gets larger. Probably because they live in a more massive halo. Okay, once again. You also see a bunch of galaxies here. These are interlopers. They are galaxies that live in your cylinder, but they happen to have nothing to do with the halo. They just happen to live along the line of sight. Well, you can sort of see them by eyes, or you can sort of correct for that. And what people typically do, the same as with the lensing, you can't go to an individual galaxy and have one or two satellites and from that infer velocity dispersion. That doesn't work. It's too noisy. So you need to stack data. So the way you do it is here, you take this data and take a little bin here in luminosity. And for all these galaxies, you plot the distribution of delta V, and then you measure the dispersion of that. Okay. And then you slide that red window across, and you get a bunch of measurements of the velocity dispersion as a function of luminosity. And this is sort of what it looks like. And again, you go to brighter galaxies, the central satellite galaxies seem to be moving faster, indicating they live in more massive halos, once again. Okay. At least you get consistent results there. Okay. And in principle, what you can do is you can do the same sort of modeling. And several people have done this. Johannes Lange has written a thesis on this. You can model this stuff and also constrain a conditional luminosity function in the same way as you did with lensing. Okay, so these are all the different methods that people are using. This plus other ones. I haven't even mentioned, for example, redshift space distortions, simply because I have a limited amount of time, but that's another method that people use. So now I'm going to talk about what have you learned from all this. So I think here sort of is a nice summary of one of the things that really we have learned very solidly. This is from a nice review paper by Peter Baruzzi, 2013. And what he's plotting is on the x-axis halo mass, and on the y-axis stellar mass divided by halo mass of the central galaxy. That is the stellar mass of the central galaxy divided by halo mass. All the different curves are different methods applied to different data. Okay? Some use abundance matching, some use clustering, some use an HOD or a CLF. All these different methods. And look how well they agree. Okay, this is astronomy. This is a factor 2. That means perfect agreement, right? This is not particle physics, right? So this is like awesome. Look at this. And not only that, you see there's something weird in this characteristic shape, but there is something weird going on. If you look at 10 to the 12 solar masses, there's a pronounced maximum there. Okay, so at a 10 to the 12, you have the largest amount of stellar mass per unit halo mass. So apparently, at a Milky Way-like mass of 10 to the 12 solar masses, galaxy formation is most efficient in producing stars. Why? That's a whole different story. That's what the data tells us. Okay? How efficient is it? Well, not very efficient. Because only here, the top, it's only about 3% of the halo mass. Now, the universal baryon fraction, as you guys all know, being cosmologists, is about 17%. So that means at maximum efficiency, I'm only turning about 20% of my baryons into stars. 80% are still out there, maybe in the halo, maybe blown out of the halo, who knows? Okay. Now, if you go to the more massive end, you see that the efficiency of star formation plummets, goes down. Why is that? AGN feedback, maybe? At the low mass end, it goes down even faster. And we think it has something to do with supernova feedback. And basically all of galaxy formation is about trying to understand how these processes create this curve. Okay, that's basically what galaxy formation does. So here we are. We have empirical constraints on it, and this constrains galaxy formation. If you're interested in galaxy formation, it's your job now to figure out why it has this function. What about satellites? Another thing that we get out of this sort of work is we can figure out what fraction of galaxies of a given luminosity are satellites. Question. And that's shown here. So this is from early work. This is B-band luminosities from 2DF. This is from Sloan. What is plotted is the satellite fraction as function of luminosity. Okay, and these are constraints. So the blue comes from the clustering, the red comes from galaxy-galaxy lensing by Rachel Mendelbaum. And I want you to sort of let this sink in for a minute. What you see is that at the very bright end, the satellite fraction is very, very small. It means the vast majority of all the brightest galaxies in the universe are all centrals. Kind of makes sense, I guess. But then by the time you go to fairly faint galaxies, this is sort of an LMC type luminosity here. The satellite fraction is only about 30–40%. And the first time you sort of see that result, you go, hold on, how can the satellite fraction be less than the central? At each halo, you have at most one central, but you can have way more satellites. So shouldn't the satellite fraction be larger than one? And the answer is no, because if you're a central light in a central, or if you're a central galaxy of a given luminosity, okay, you live in a particular halo mass. But if you're a satellite galaxy of that luminosity, you live in a much more massive halo, of which there are way fewer because of your halo mass function. So that's why, although each halo has more satellites than centrals, the satellite fraction is still less than unity. Anyway, we have it nicely constrained. It's only 30%. So that's another reason what you learn from this. If you look at the whole galaxy population, you're mainly looking at centrals all the time. Okay. All right. Here's another thing that we've learned really well. What is the scatter in the stellar mass-halo mass relation? I told you we have this sort of curve, right? And we agree. What I'm talking about is not the scatter between the different measurements. I'm talking about for a given measurement, a given constraint, what do we think the scatter is? Right? Because at a given halo mass, not all centrals have the same luminosity. There's some scatter in there. We can actually constrain that. Satellite kinematics are particularly good for constraining that. This is from a paper by Surut More, who used satellite kinematics to do this. And here are the constraints on the scatter, sigma log L, and it's about 0.1, 0.2 dex. This was back in 2009. Here is recent work that I'm working on with Gustav Mitra, who was supposed to be here, but then his visa didn't get in time, sadly. Again, satellite kinematics, but a new method. And here in blue are our constraints. Again, 0.15, 0.2 dex. Solid dots and yellow dots are all from different studies, including Johannes Lange analysis. Here is actually a comparison between these kind of constraints and simulation results. The blue line is the Eagle simulation. Okay, it's one of these hydrodynamical simulations. And you see it sort of predicts again of the order of 0.15, 0.2 dex scatter. And over the region where it's measured, okay, it's in good agreement with the measurements. So I think we can safely say that there's a good consensus at the moment that at least down to this luminosity, down to halos of about 10 to the 11, 10 to the 12 solar masses, the scatter is actually fairly small. It's only 0.2 dex. Okay, so galaxy formation is not wickedly stochastic and random. Okay, and this is again confirming one of these key premises that we made, right? That there is some galaxy property that is tightly correlated with the halo property, tightly with about 0.2 dex scatter. That's how tightly it is. So again, this scatter is pretty darn well confirmed. There's one thing I want to point out, though, that here is a stellar mass, halo mass. So this is the stellar mass of a central as function of halo mass. This is the average relation. Again, there's that broken power law. Okay. And this scatter, this is sort of the scatter that I was referring to, a scatter of 0.2 dex. So this is what it looks like in this plot. And what I'm doing here, we believe that this scatter is roughly independent of halo mass. At least that's what we have inferred from the data so far. And you can sort of see, if I move these up, the scatter is everywhere the same. Okay. But if you flip this around, you ask, what is the scatter in halo mass at a given stellar mass? You get the following. Okay. So now you go here, and at this stellar mass, because the slope of the stellar mass halo mass ratio is so shallow, we have a huge scatter in halo mass at this stellar mass, whereas here the scatter is much smaller. So if you ask what is the scatter in halo mass at a given stellar mass, that has a very strong mass dependence, and it blows up if you go to more massive galaxies. Again, simply a consequence of the fact that the stellar mass halo mass relation gets very shallow at the massive end. And this is important for you to realize, because when people do stacking, when you stack galaxies, say you stack many galaxies of a few times 10 to the 11 solar mass together, you are stacking halos that span a huge range of halo mass together, right? You're stacking systems together that have halos that go from a few times 10 to the 11 all the way to 10 to the 15 solar masses. Right? So be aware when you stack that you're combining halos of very different masses. That's the only thing I wanted to point out here. All right. That's what I said. All right, now finally, cosmology. Can we do cosmology with this? And the answer is, of course, yes, otherwise I wouldn't be here. So here's a sort of an illustration of what happens if you change sort of cosmology. Now, this goes back to the old days when we just had WMAP 1 data and then WMAP 3 data came out. WMAP 1 means the first year data release of WMAP. Okay. Back in those days, WMAP 1 said, okay, omega matters 0.3, sigma is 0.9. That's it. Okay, and that's what everyone was working with. And then a few years later, WMAP 3 came out, and the cosmology changed quite a bit. It went from omega matter 0.24 and sigma to 0.74. Now, what I'm plotting here is the difference in the halo mass functions between those two cosmologies. And it doesn't look dramatic, but remember, there's 8 orders of magnitude here. So there's a quite strong difference in the halo mass function between these two cosmologies. But also the halo bias is different. Okay? The halo bias function depends on cosmology, and that's also very different. And the concentration mass relation for halos is different, because in different cosmologies, things assemble earlier or later, and that sets the concentration of the halos. So if I do fit my clustering in one model, for one cosmology, I can get a fit to the data, I get an infer stellar mass halo mass relation. But if I change my cosmology, all the ingredients change, and I probably should get a different answer. And now 2 things can happen. If I go from one cosmology to the other, either I certainly can't fit the data anymore. Wow, that's awesome. I can rule that cosmology out, probably, hopefully. Or I can still fit the data, in which case I have a degeneracy. Well, which one is it? Well, sadly, the latter. So here are constraints on the mass to light ratio as function of halo mass. This is sort of confusing. I remember I showed that plot by Baruzzi et al, where he plot stellar mass over halo mass. So he had a maximum at 10 to the 12 solar masses. Now I'm plotting halo mass divided by stellar luminosity. Okay, so that's the inverse. So now I have a minimum around 10 to the 12. But these are the constraints that you get on the stellar mass halo mass relation by fitting the clustering of Sloan, okay, for these 2 different cosmologies. And most importantly, the fits are equally good. I can look at those fits and I can't tell which one is better. WMAP 1, W3, I get equally good fits. I get very tight constraints in both cases, but the constraints are mutually inconsistent. So which one is it? You know, if you are interested in galaxy formation, you want to know, how big, what is the luminosity to give a halo mass? This one or this one? Well, it depends on your cosmology. Oh. But here's the good news. These differences are mainly differences in the mass at a given luminosity. So if we can come up with another method that independently measures mass, we can maybe break the degeneracy. Okay. Here's another illustration of the same idea. A very nice paper by Jeremy Tinker. Here's a data, WP, clustering as function of radius. The symbols are the data. And he is showing a fit to the data for 4 different values of sigma 8. And you can see all fit equally well. The dashed line, by the way, are just the dark matter correlation function for comparison. Okay, so you see the dark matter correlation functions are very different. But just by putting galaxies in different halos, I can still fit the clustering of the galaxies equally well for all 4 cosmologies. Of course, it means I have to put the galaxies in slightly different halos, so my halo occupation model is different for the 4 cases. It doesn't look like a lot, but again, this is a logarithmic plot. Okay, what you can show is now the mass divided by the number of satellites, normalized in some way to make it unitless. That is very different for those 4 models. So if you can somehow constrain the mass better, you should be able to break the degeneracy. Okay? And then you can do cosmology. And that's sort of the idea. Okay? So how can you do that? Oh, thought I had something more. Here's another result of that. Let's go back here. Right? What you see is that these models for these different cosmologies predict very different mass to light ratios on sort of the cluster scale. So back in 2004, when we started playing this game, when we started fitting clustering, and we got these sort of, we noticed that there was this dependence on cosmology, we realized that there were actually constraints on the mass to light ratios of clusters out there. People had measured that with X-ray data and with satellite kinematics. So we said, okay, can we use this? So what we did, this is back in 2003, actually. Omega matter, man, bloody hell, that's a long time ago. Omega matter sigma 8. And these are the constraints that we got from fitting the clustering data from 2DF. So we get pretty lousy constraints, but at least we can rule out some parts of parameter space. But other than that, everything here goes. Interestingly, this was a good agreement with the Kobe results back then. That was even before WMAP. Okay? So, okay, we get some constraints, but not much. But each of these models, here's, by the way, WMAP 1 and WMAP 3, they lay here for comparison. For each of these models, I predict a very different value for the mass to light ratio on the scale of clusters. Again, I can fit the clustering equally well, but I have to put galaxies in different halos, and therefore the mass to light ratio on the clusters differs. And it differs by quite a bit. Now, the good news is, back in those days, we had constraints on that, and there was about 350 plus or minus 70 that lies in this band. And you can clearly see that's completely inconsistent with the WMAP 1 cosmology. It sort of tells you want to have a lower sigma 8. So back in 2003, this was an early manifestation of what is now known as the S8 problem, okay, the S8 tension. It was already evident back then. Okay, and there's several other studies that have pointed out similar things in those days. Anyways, here's the upshot. If you want to break the degeneracy between cosmology and the galaxy halo connection, you need to combine clustering with methods that directly constrain halo mass. And there's basically three methods out there. One is galaxy-galaxy lensing. It directly is sensitive to mass. The other one is satellite kinematics, as I mentioned. And the third one, which I haven't mentioned, is redshift space distortions. Redshift space distortions basically are due to the peculiar velocities of the galaxies. And where do the peculiar velocities of the galaxies come from? They're sourced by mass. So again, that's a way of measuring mass. So there's mass dependence there. Now, I don't have time to go and talk about all of these. I'm going to focus on the combination of clustering and lensing, because I think that's sort of the most common thing that people have used. So we're going to look at, if we now combine clustering and lensing, what are we going to learn? Okay, so remember galaxy-galaxy lensing, that's what it looks like. And I showed you this plot. And I actually lied a little bit because I said this was the best fit to the data that we got. That's not true. What we actually did was we had a fit to the clustering for both the WMAP 1 and the WMAP 3 cosmology. We had fit the clustering. And for those models, we can now predict what is the lensing. And for one of the two cosmologies, this was a prediction. And for the other cosmology, we got the other prediction. So we had two models, both fit the clustering equally well. They predict different mass to light ratios. We use those models and we predict what the lensing should be. We're not fitting anything to the data. One is bang on. That's the one for the WMAP 3 cosmology. For the WMAP 1 cosmology, it's significantly off all the time. So clearly, the combination of clustering and lensing allows you to constrain cosmology. And it tells you, hey, you want to be omega WMAP 3, low sigma 8. So this prompted this sort of work. So here, 2013, we got some nice constraints on omega matter sigma 8, okay, sort of in between WMAP and WMAP 3. And when we published this result in 2013, this was a CMB constraint. This was WMAP 7, I think. And there was no tension to speak of. So we never screamed, tension. We said, okay, it's a good agreement. But then these bastards from CMB, they decided to change their results, and Planck comes along and comes up with these results. Okay? And then, the story continues, and DES year 1 release comes around. Look at their constraints. They're very large, very poor compared to our constraints from earlier. It's not because the data is poor, the data is way better. But what the DES year 1 analysis did, they decided, this nonlinear scale stuff, that's really hard. We're going to throw away all data below 5-6 megaparsecs. We're nicely in the linear regime. That's more robust. It's probably a reasonable thing to do, but you're throwing away a lot of data and you lose a lot of constraining power. Nevertheless, there was a hint of a tension. And then, of course, Planck continued to improve their results. Okay. And Johannes, for his, I think this was after your thesis, Johannes, did a nice analysis of Bosch and came up with these results. And now we start to really see this tension. Okay. And it's become known as the S8 tension. S8 is just a combination of omega matter and sigma 8. And it moves in this direction. Oh, sorry. It moves in that direction that was indicated by the arrow. Okay? So that's the S8 tension. And there have been many papers on this. Okay, here's another one based on lensing by Alexis Leteau. Okay, so here's the Planck result, and here are the results from lensing, from kits, and from other data sets. More constraints, again, Planck versus other lensing constraints. Here's a very nice analysis by Amon based on the Dessier 3 analysis, so S8 versus omega matter, Planck, and their constraints. And the tension continues and continues. Here's a very nice paper recently by Johannes Lange, summarizing this here in blue. That is the CMB constraints on omega on S8, and all the other different measurements. None of them are really like 3, 4, 5 sigma significant. But if you take them all together, there's a clear tension that all of them sort of hint at a much lower value, significantly lower value of sigma 8, S8. Another way that this is sort of manifested is in what is known as the lensing is low problem. It's basically the same problem. Okay, don't confuse these. They're not two different problems. It's one and the same thing. But here's what Alexis did. So Alexis said, okay, let's assume Planck is right. Let's now go and fit the clustering for the Planck cosmology and use that to make a prediction for what the lensing should be. And then you get these predictions. And this is where the data is. So when she says the lensing is low, she means the data is low compared to what you would predict for a model, assuming the Planck cosmology that is fit to the clustering. But that's too long, so lensing is low is easier than that entire thing. Lensing is low, that's the problem. It's the same as the S8 problem, okay? All right, so to summarize then, and then we'll break quickly, there is a persistent tension between the observations in the clustering at the low redshift universe and Planck, CMB results. So what's going on? Well, maybe Planck is just wrong. Right? Now, I don't think that's true. Okay, there is a tension also with the Hubble parameter, of course. Maybe there is something interesting going on, but I don't think Planck is doing something wrong. So maybe then the really cool stuff, maybe we're seeing evidence for new physics beyond the vanilla lambda 6-parameter model. In particular, non-zero neutrino mass, remember from yesterday, can suppress the power on small scales. That can actually look like an S8 tension. Maybe this is evidence that the neutrino mass, we can now measure the neutrino mass. That would be a really cool paper to write for Nature, right? But you better make sure that it's not one of the other things. Okay? Make sure there's not systematic errors in the lensing shear measurements, because that's really, really hard measurements. And initially I thought that must be it. But now, many years later, many different studies, different analysis, different data sets, they all point to the same thing. I don't think there's something wrong with the lensing anymore. It's probably robust. So that then leaves maybe the systematic errors in our modeling, our beautiful analytical modeling. And after the break, we'll discuss that. So let's break for about 10 minutes and then continue. Which is good. All right. So throughout, we have assumed, so there's two effects that I want to mention. Okay, one has to do with baryons, these really dirty things. And the other has to do with assembly bias. So baryonic effects. So we have assumed throughout, guided by what the M-body simulations tell us, that dark matter halos have a beautiful universal NFW profile. Okay, that's true in the simulations with dark matter only. You run a hydro simulation, you add baryons. What's going to happen is these baryons are going to cool in these halos and they sink to the center, and all the gas is going to accumulate there, and gravity operates and it pulls the dark matter in, and that's called adiabatic contraction. And then stars form, and then supernova feedback is going to blow the gas out, and suddenly the gas is going to be slingshotted out of the halo, and all sorts of stuff happens. And at the end of the day, your halo mass and halo density profile are not the same anymore. They don't look like an NFW anymore. The halo mass has changed because I have blown gas out of my halo. I've reduced the mass. And depending on how feedback operates, I can change the mass profile. I can do a lot of things. Here's a nice paper showing the mass of a halo in a hydro simulation compared to the mass of the same halo in the corresponding dark matter only simulation. Okay, as function of that mass in the dark matter only simulation. And you can see these are for different simulations, different colors. But you see that, you know, there are variations of about 20%. The halo masses have changed by 20% on average. And the worst part is 3 different simulations, they don't agree. Each simulation gives you a different answer because they treat the subgrid physics differently. So in principle, you can say, okay, this effect is there, but all I got to do is look at a simulation, and that simulation will tell me how I can correct my masses for the baryonic effects. Well, depends on which simulation you pick. Here's another thing. It changes the power spectrum of the mass distribution. We had this wonderful thing. We could compute the nonlinear matter power spectrum analytically, no simulations needed, except we ignored the bloody baryons. You put the baryons in, and you measure the matter power spectrum in a hydro simulation, and you take the ratio. So here's dark matter plus baryon power spectrum divided by that in a dark matter only simulation. Here's 1, that's good. Okay, at very large scales, baryons don't do much. But once you drop below a scale of about 10 megaparsecs, things start to change. Again, different curves, different simulations. Which one do you pick? What's going on here, by the way? Actually, you can, on very small scales, the power gets larger. It's because on very small scales, basically galaxies have condensed at the centers of those halos. They've added more power on very small scales. The density fluctuation have gotten larger. On intermediate scales, you have a dip in this thing, and that's due to supernova feedback and AGN feedback having blown out gas out of the halo, displaced it to larger distances. But you can see different simulations get very different results. So you can't be guided by the simulation to tell you how to correct for it. So how do we deal with this? This is a huge problem. Okay, look at the magnitude of this effect. This is 20, 30, 40%. We want to measure the power spectrum at 1% accuracy. We can measure it. The data is good enough to do that. Our models better match that up. Here's an uncertainty of 20%. And there's no consensus on the magnitude of this effect from the simulations. The next question, of course, is, oh, might this have something to do with our SA tension or lensing is low? Here's a very nice study by Johannes Lange. So what is plotted here is, again, this lensing is low idea. So this is the prediction for what the lensing should be for a Planck cosmology that's fit to the clustering, ignoring baryonic effects. Okay, that's sort of what I was showing. And here's the data. So this is the lensing is low problem. The lensing data is low compared to the prediction. But then Johannes said, okay, let's now modify the prediction using from a simulation what the actual density profiles of the halos is. Okay, and then for different halo mass bins, here are the results for different simulations. It's the illustrious simulation, and this is the TNG 300 simulation suite. Okay, and what you see is that, hey, it helps you in reducing the tension. It goes in the right direction, but not far enough. But at least it goes in the right direction. And it's about 10% effect if you believe TNG 300. If you believe illustrious, it could be almost 20% effect. Now, illustrious is probably not correct because they had an extreme AGN feedback model. But it does go in the right direction. So it reduces the tension if you take the baryonic effects into account. Again, this is just using one simulation. Maybe there's other simulations out there for which the reduction is more or less. So here's the main challenge, as far as I can see. I think there is, and I think most likely there always will be, a lack of consensus. There is consensus. No, there is no lack of, I forgot no. The most important word is missing. There is no consensus, nor will there ever be, about the magnitude of this effect. So how are we going to deal with this? And I think there's basically two ways forward. Either we're going to say, okay, let's assume that the simulations bracket the truth. The real thing is sort of in between these extreme ideas that the simulations give. And then we can say, okay, then somewhere in here is the answer, and let's just marginalize away this uncertainty. Let's marginalize over the uncertainty. The problem is it's a 20% uncertainty. You might as well stop taking data because the data is so good that, 20%. So it's like equivalent to throwing away all your data on small scales. So that's kind of sad. We spend $1 billion going to get all that data, and we're going to throw 80% of it away. So what else can we do? Well, maybe when these simulations make different predictions for the strength of this effect, it's because in one simulation they blew the gas out to larger distances than in other simulations. So if we could simultaneously measure the gas profiles around galaxies, we might be able to tell and break this degeneracy. But hold on, that means now I have to simultaneously model not only my stars, but I also have to model the gas distribution around the galaxies. And that's where you get very depressed. At least I do, because I have no idea how to do that with any sense of secure, accuracy. Nevertheless, some people are brave and are taking that approach, trying to do this. Okay, and there's forthcoming data, like SZ effects and X-ray data that will give us some idea about the average gas profiles around galaxies, but it's going to be a very, very, very difficult road. So that's baryon effects, which is the lesser of the two evils. Now we go to assembly bias. First, there's the thing called halo assembly bias. So what is halo assembly bias? We have always worked with this idea that, hey, halo bias depends on halo mass. More massive halos are more strongly clustered, which is all true. But in 2005, a very nice paper pointed out, yeah, but let's now take halos of a given mass and split them in old halos and young halos. Now, what do you mean by old halo and young halos? Halos, here are the mass assembly histories of halos of a given mass, and there's a lot of scatter in them. Some assemble early, they're called old halos, and some assemble late, they're young halos. And if you split your halo population in the old ones and the young ones, and you just plot their distribution on the sky, yesterday that's what you guys have been learning how to do, you see by eye that they're clustered differently. This is a wickedly strong effect. So what this tells you is that the clustering strength of halos does not just depend on halo mass. At fixed halo mass, it depends on the assembly history of the halo. Uh-oh. Okay. Now, that's one thing. A few years later, Risa Wexler shows, hey, how about we don't split the halos by assembly time, but by halo concentration? And we can do this at different mass bins, and we split it in quartiles, the highest concentration, the intermediate ones, and the lowest concentration, and measure their relative clustering strength. Okay? If there's no dependence on concentration, this should be 1. And well, it has a complicated dependence. It flips around with dependence on mass. In one mass scale, the low concentration halos are more strongly clustered. And another mass scale, it's flipped around. This is a disaster. It got worse and worse because then people start, okay, that's nice. That's it depends on assembly time. It depends on concentration. What about the spin parameter of the halo? Yep, clustering depends on the spin parameter of the halo as well. It depends on the shape of the halo. It depends on the environment of the halo. You name it, you think of any property of a halo, I guarantee you the clustering strength depends on it. That's basically the lessons we've learned. And what we're just learning is clustering strength is actually a rather poor, at least not a clean indicator of halo mass. And that's the entire premise that underlies what we've been doing all this time. We're using clustering strength as an indicator of the mass of the halo in which these things live. So that's bad. Now, as a little aside, you can ask, why do the halo clustering strength depends on all these properties? And briefly, It's an interesting question, so that's why I want to say a few words about it. First of all, part of it is the fact that halo properties are all correlated with each other. And I told you that the formation time of a halo is correlated with the concentration. Halos that assemble earlier are more concentrated, right? So if you find that the clustering strength at a given halo mass depends on formation time, it should also depend on concentration, because concentration and assembly time are correlated. Okay, so part of these dependencies come from that. Okay, so halos of a given mass that assemble earlier are more centrally concentrated. Turns out that they actually have a somewhat smaller spin parameter. Turns out that they have less surviving substructure. So the abundance of satellite galaxies is probably going to depend on that. And they're typically more spherical. So that explains at least part of why this clustering strength seems to depend on every freaking halo property. But it also has probably to do with environment and from tides from nearby halos. If you're a halo of 10 to the 12 solar masses and you live next to this ginormous 10 to the 15 solar mass halo, you would like to grow and get more mass, but it's all taken by that big guy next to you. The tides pull all the mass to the big guy and your growth is arrested. You can't really grow anymore because you have this big guy next to you who takes away everything, right? Whereas if you're a halo and you live in a void, you're the biggest halo in the neighborhood, whoosh, everything goes to you and you continue to grow. So now you can see that halo growth, it depends on environment just due to the tides. And there's a similar effect having to do with splashback halos. You may have heard of that. Okay, some galaxy subhalos come in, they fly through the halo, come out of the Virial radius. Okay, they go out about 2 Virial radii and then they turn around. But there's a long period of time where they live between 1 and 2 Virial radii. We typically call those things host halos because they live outside of the Virial radius. But for all practical purposes, they have just went through the halo. They have lost a lot of mass. Their mass is now less than what they originally had. So now you have a low mass halo living next to a big halo, but it's not really a low mass halo. It was a big halo, it just lost mass. So that causes all sorts of effects. So it's actually not really hard to understand why clustering strength of halos should depend on all these things. It just makes it extremely hard to model this. So what do? Well, first of all, I should point out when it gets really bad. So halo assembly bias is what I call the fact that the clustering of halos at fixed mass depends on secondary halo properties. Now, I admit a more logical name should be secondary halo bias, and some people use that term. But the first assembly bias that was detected was with the assembly time, and therefore that has stuck. So people use the word halo assembly bias to describe the dependence on any secondary halo parameter. It may be confusing, okay, but just be aware of that nomenclature glitch. Then there is the mass-only ansatz. That is basically the premise that we have used throughout. We have continuously said, let's assume that our halo occupation statistics depend on halo mass and on halo mass only. We've only made it depend on halo mass. But what if the occupation statistics of halos also depend on the assembly time of the halo? Well, then we have what is called galaxy assembly bias. So galaxy assembly bias is a phenomenon that at fixed halo mass, the occupation statistics depend on secondary halo properties that show halo assembly bias. And that sentence in formula, so if the probability for a given halo with mass m and property x to host a galaxy is not the same, depends on x, and x is a parameter that controls the clustering strength of the halos, then we have a problem. Then that is something we have ignored so far in everything we talked about. And that's called galaxy assembly bias. Okay. Basically, galaxy assembly bias is the violation of the mass-only ansatz. Okay. Now, why do we care about this galaxy assembly bias? Well, first of all, if you're interested in galaxy formation, you'd like to know if certain galaxy properties are correlated maybe with the assembly time of the halo or the spin parameter of the halo. That tells you something about galaxy formation physics. So if you're interested in galaxy formation, you want to know this. For our purpose, here's the issue. Let me give you an example of where things can go really bad. Here's an empirical fact. Red galaxies of a given luminosity are more strongly clustered than blue galaxies. In the standard mass-only ansatz, there's only one explanation that can explain that. Those red galaxies must live in more massive halos. But if you allow for galaxy assembly bias, there's an alternative explanation. No. They live in halos of the same mass. The red galaxies just live in the halos that assembled earlier. And that's why they're more strongly clustered. And that doesn't even sound like a crazy idea, right? If the halo assembles earlier, maybe the galaxy assembles earlier, and then all the galaxies are redder. So now suddenly you have a degeneracy. Bloody hell. What are we going to do with this? And finally, and most importantly for us here, this can also bias your cosmological inference. And of course, this brings us to the $64,000 question. Might the SA tension be a manifestation of galaxy assembly bias? So how can you model galaxy assembly bias? Well, in principle, you just have to make it a little bit more complicated, you would think. You just go from this and you just add a dependence on a second parameter. Or maybe a second and a third and a fourth. But this is easy to do. You can come up with a model here. But we also need to quantify how the bias of the halos depends on that secondary parameter. And although for the halo dependence, the halo mass dependence, we have an analytical prescription, we can use prosector theory. For any of the other secondary parameters, no, we don't. We don't know how to write this down for any cosmology, at least not to my knowledge. So what does that mean? That means we have to use simulations to do this. And this entire thing that I was so excited about is out of the window. We have to go back to the simulations because there, all this halo bias stuff is baked in. Okay, so now we have to use simulations again. So here's an example of how you can do this. This is decorated HOD model. It was developed by Andrew Heron. So you say, okay, I'm going to add a dependence on a second parameter, which can be concentration, say, of the halo, or the assembly time of the halo. And I'm going to say that I'm going to split my population of halos in two, the ones that have a high concentration and the ones that have a low concentration. And the ones that have a high concentration, I'm going to offset the typical HOD model by a certain amount, and in the other ones, I'm going to offset it in the opposite direction. And pictorially, what it looks like is like this. So here is a model without assembly bias. Okay, so I have old halo, young halos, but the occupation statistics is the same for them. This is halos of a given mass, and on average, you have 2 galaxies per halo. Okay, now I have one free parameter that I add to it, and I can dial it up and down. And if I dial it all the way up, I still have on average 2 galaxies per halo, but all of them only live in the old halos, or the high concentration halos. If I dial it all the way down, I still have 2 galaxies per halo on average, but now they live all in the other class of halos. So I just add one free parameter to my model, and you can see I have a large amount of freedom now in how I shuffle my galaxies around. And if the old galaxies and the young halos are clustered differently, I'm going to get different results if I dial my A bias up and down. So I've added a degree of freedom, and I can just add that to the model and see what does it do. There's a whole bunch of other things that people have invented over the years. There's ground HOD. You can inject an X dependence into the HOD parameters. There's flexible abundance matching, conditional abundance matching. The literature is exploding in this field, which is a good thing. Okay. Now, do we expect galaxy assembly bias? Okay. Some people, right, this field for a long time has ignored this. We knew this in 2005 that this problem existed. And this field has plowed on for at least 10 years, just completely ignoring it. Go like, well, you know, there is no evidence for galaxy assembly bias. And often the argument was, well, we can fit the data without adding it, so there's no need for it. That's a nonsense statement, of course, because we're completely getting biased results. So first of all, let me point out, there's absolutely no reason to assume that there is no galaxy assembly bias. The idea that galaxy formation efficiency should only depend on halo mass and nothing else of the halo, come on, right? It seems only logical that the properties of a galaxy depend on the assembly and the shape and the spin parameter and the angular momentum of the halo. Secondly, for what it's worth, both the semi-analytical models and the simulations actually predict, if you can use that word predict, that there is different levels of galaxy assembly bias. Here's different simulations. The emerge model by Ben Moster. Here's the Eagle simulations, plotting stellar mass as function of halo mass. And you see that at a given halo mass, the scatter in the stellar mass halo mass is correlated with the concentration of the halo in which they live, or with the formation time of the halo. And that is galaxy assembly bias. That scatter in the stellar mass halo mass relation is correlated with a secondary parameter that controls clustering strength. So if the SAMs and the SIMs predict it, and we have no reason to assume that it doesn't there, it probably is there. So can we observationally detect galaxy assembly bias? Well, this is where it gets trickier. So how do you do that? Ideally, you want to do a direct detection, and that requires a demonstration that different subsets of halos of the same mass are clustered differently. Okay, so pictorially, we have this stellar mass halo mass relation. You want to pick the galaxies here at A and the galaxies at B and show that they're clustered differently. If you can prove something like this, you have proven that assembly bias exists. Okay, so this is just an illustration. It's not real data. I'm just making this up. Yeah, but that's the idea of what you want to do. Now, a few years ago in 2016, there was a very nice paper who actually did this. They had a bunch of clusters, okay, and they split the clusters in depending on the average radius of the member galaxies away from the center. So large RMM and small RMM. Small RMM means the galaxies are concentrated towards the center of the cluster. Large RMM means they're more in the outskirts. Okay, that's like a secondary property of the galaxy. And then for each of those systems, they had these two classes. They measure the average mass using galaxy-galaxy lensing. And that's shown here. So this is delta sigma for the two samples, and the yellow dots are actually copied down here. And you can see they give the same lensing signal, and therefore they must have the same mass. So apparently we have here two subsets of clusters that have the same mass according to lensing. Let's look at the clustering. And here's the clustering relative to each other, and they're clustered completely differently. So apparently the clustering strength has something to do with RMM. That is galaxy assembly bias. So this was claimed to be a solid detection of galaxy assembly bias. Unfortunately, first of all, the signal was larger than expected because actually at the very massive end, we don't expect much assembly bias. Assembly bias is much stronger at the low mass end. So this was actually a signal that was stronger than expected. And secondly, people have actually shown you can explain this effect with projection effects. Okay, maybe the small RMM clusters are clusters that are sort of seen end on, and then the fact that you have a stronger clustering. I mean, I don't know the details, but there's several papers have pointed out, no, this is not a solid detection. You can explain this. Okay, these things do not necessarily have the same mass. There's projection effects that come into play. So okay, so that didn't work. I at some point was involved in a paper where we claimed a smoking gun of central galaxy assembly bias based on galactic conformity. Galactic conformity is something that if you go and you look in a halo and you look at the central galaxy and you find that the central galaxy is red, turns out the satellites on average are more likely to be red. So the color of the satellite galaxy seems to know about the color of the central. That's conformity. And if this is within a single halo, you call it one halo conformity. And if you can measure this on larger scales, it's sometimes called two halo conformity. And the fact that now the colors of the galaxies seem to know about the colors of nearby galaxies, that's like not consistent with the halo mass only ansatz. That would be an evidence for galaxy assembly bias. Well, again, people went back and forth, and group finder errors, projection effects can all make this look, make this appear without real galaxy assembly bias. So I say this is an ongoing debate. And it's an ongoing debate because the real challenge is, if you want to prove this, this direct detection, you have to do it at a fixed halo mass. But halo mass is not direct observable. So we use some proxies for halo mass and then try to prove that they are the same halo mass, and then all sorts of things go wrong. So this is hard. There's another way which people do this, which is indirect detection. Okay? Indirect detection says include galaxy assembly bias in your occupation model, like with the decorated HOD, and just leave that parameter free. And if your data needs assembly bias and it can't fit it without, then you can claim to have detected assembly bias. Okay? Here's an example of something called decorated HOD, conditional abundance matching. This is a very nice paper. When I first saw it, I couldn't believe it. Andrew Heron, Doug Watson, what they did is they did abundance matching, okay, and standard way, and they showed that it could fit the clustering of galaxies in different magnitude bins. People have done that before. But then they decided, okay, now let's pick all the galaxies in a given luminosity bin. Okay, they live in all different halos. You go into the simulation, you find all the halos that have a galaxy of that luminosity after abundance matching. And you rank order those halos by their assembly time. And then you say, okay, but those galaxies in my luminosity bin, they have a distribution of colors in the data, in Sloan data. And you rank all the colors of those galaxies. And now you say, okay, I'm going to assume that the oldest halo has the reddest galaxy. And you do it in each luminosity bin. That's called age matching. Simple exercise. They just did that. And then they said, now let's predict what the clustering of the red and blue galaxies is. And it fits amazingly well. So what they have assumed is that the color of the galaxy depends on the formation time of the halo. That is galaxy assembly bias. So here's an example where they have included galaxy assembly bias and showed you get a perfect fit to the data. Is that proof? Unfortunately, no, because we had already known this thing about red galaxies and blue galaxies being clustered differently, and people had gone out and tried to measure the halo masses, okay, at a given stellar mass for red and blue galaxies. And this is with satellite kinematics. And what you see is that you find actually that the red galaxies have even more massive halos than the blue galaxies. And the same thing here. This is from galaxy-galaxy lensing from Rachel Mandelbaum. Again, the red galaxies are inferred to have bigger halos, more massive halos than the blue galaxies. That could also explain why the red galaxies are more strongly clustered. So again, you run into these degeneracies again and again and again. Okay? So there's a degeneracy, and that makes it really hard to unambiguously detect galaxy assembly bias. Don't get me wrong, I'm not arguing that we can ignore galaxy assembly bias. I'm convinced it's there. Okay? It's just very hard to model it and to deal with all these degeneracies. You can try and think about, okay, what is the best observable to break these degeneracies? And Quan Wang has done some really nice work, and she has actually, this is from her paper, has shown that probably the best statistic to combine with clustering is counts in cells. So this is the error on an assembly bias parameter. Okay, if you just use a clustering plus lensing, and here's clustering plus counts in cells, and you get a better constraint on assembly bias. It's a better way to constrain it and to detect it. Of course, the real answer is use everything. Okay, then you get an even better result. Okay. So I'm almost done. There's 2 or 3 more plots. So first, here is now the important question. Can galaxy assembly bias get rid of the S8 tension? So here again is this work from Johannes Lange. So this is again the same thing. He fits the clustering, okay, and then this is a prediction for the lensing, and this is where the lensing data is. This is the standard lensing is low problem. And this uncertainty here, that's the uncertainty from his posterior of fitting an HOD to the clustering. Okay, and then over that posterior, you now make slightly different predictions for the lensing. Okay, and that's what that gray, blue, what is it, red region indicates. And then Johannes did the same thing, but now he used decorated HOD model. He added 1 free parameter and redid the exercise. And this is what you get. You can use a different secondary parameter. You can use concentration or spin parameter. And you see, you now have more freedom in fitting the clustering. You have an extra free parameter. So now your predictions for clustering are also, have a larger uncertainty. And most of that uncertainty goes in the right direction towards solving the tension with lensing is low. Not entirely. Even the most extreme assembly bias models don't come as low as this. So, but again, that is just one particular treatment of assembly bias. Here's another one, very nice paper by Sandy Yuan. Again, the lensing is low model. This is a model without assembly bias and adding different kinds of assembly bias, environmental dependence, and I forgot what this one was. You add more and more assembly bias dependencies into the model, you come closer and closer and closer to the data. Maybe this problem is not there. So is assembly bias unable to explain the lensing discrepancy? It helps, but it doesn't solve it. Well, here's a real problem. Johannes very nicely showed that assembly bias itself is degeneracy with cosmological parameters. So here's a model where he had a certain cosmology and he assumed a certain value for the assembly bias parameter, made a mock data set. This is the truth, okay? And then he analyzed that mock data set, assuming different cosmologies. And for each cosmology, you can get nice fit to the data, but then he infers a different value for the assembly bias parameter. So, if you assume the wrong cosmology, or if you now assume no assembly bias, clearly you make an error in your cosmology because you think this is the best fit cosmology, whereas it's really this. So assembly bias parameter is also degenerate with your cosmological parameters. This is a real disaster. Here's a brand new result. Just came out while I was preparing these slides last week. It's solved. This paper uses, again, some subhalo abundance matching, and it includes the treatment of orphans, and it has a secondary halo property that is dependent on the large-scale environment. So not assembly time or spin parameter, the large-scale environment of the halo. And padam, they claim they can fit it. Not only that, they can fit it for a Planck cosmology, they can get a good fit, but for the low S8 cosmology that people have always assumed, they can also fit the data. So, hey, assembly bias is degenerate with cosmology, and it's flexible enough to solve the S8 problem, and it's so flexible that you can't constrain any cosmology anymore. All right, we're getting depressed more and more. All right, actually, here's a paper that was a year earlier that did basically the same thing, but they couldn't solve it. And I don't know why one can and the other one can't, but basically they did the same thing. They had a flexible radio profile, which is the same as allowing for orphans, and their HOD had environment dependence, but they couldn't solve it. So this is sort of the status of the field as we speak. And I want to summarize then by just, I think the only conclusion then is that, you know, we have to live with the fact that inconsistency is the only thing that we're consistent at. And to just summarize, the galaxy-halo connection is very powerful. We use it for two different things. Either we try to use it to constrain cosmology, and there the idea is that we want to have something flexible enough that we can marginalize over galaxy formation physics. That's what we are trying to do. The problem is assembly bias has become a real condemnation here. And body simulations now are a must, which really ruined it for me. But you have to deal with orphans, so the simulations are needed, but they're not perfect. The good news is emulators and cosmological evidence modeling are making this sufficiently fast that now you can do this really fast. Okay, it was, you know, a real problem, but now with emulators and Johannes came up with a really nice technique, cosmological evidence modeling, we can actually do this. We can actually use simulations and still go over cosmological parameter space. So lots of progress there. Will we ever be able to break all these degeneracies? And I'm not sure. Clearly, at the moment, we're not close. How to deal with baryonic effects? I don't know. Can we ever reach 1% accuracy? I don't know. Right? With the simulations, it comes down to beating cosmic variance, which basically means you don't want to run one simulation for a given cosmology. You basically need to run a 50 and then average over them to beat down cosmic variance. Makes it even more expensive. There are tricks around that. But this is a really big challenge, 1% accuracy. And I think the biggest problem that we're going to face, and you should all think about this question, is you're going to write your paper at the end of the day, you've done all your work, you're going to find some constraints in cosmological parameters, and then some person comes around like, yeah, but how do you know that you marginalize over all possible galaxy formation models? And that, I think, is the worst question you can get. Now, on the other hand, you guys are smart, so maybe you guys can break through this. If you're interested in galaxy formation, you just fix cosmology, Planck, done. Assembly bias is now a blessing because you can learn more about galaxy formation. You still need embodied simulations, but okay, you know, we can deal with that. You only need a few because you don't need to sample cosmological parameter space. You know what the cosmology is. You just need 5 of them and you can beat down cosmic variance, so that's good. Will we be able to break the degeneracies? Well, there's much less parameter space because I don't have to be degenerate with cosmological parameters anymore. So probably, how to deal with baryonic effects, I don't know. There's no need for 1% accuracy. We're galaxy formation, you know, anything with a factor of 2, that's good. So that's good. And finally, there's no marginalization. So on this end, everything is sunny. And on that bombshell, I'll stop here. Thank you. Time for questions, or am I late?
There was one, which, well, there were a couple, but the most prominent question is, what do you do? How do you do sub-halo abundance matching when galaxy halo is incomplete?
Yeah. I don't think you can, unless you have a very good reason to know what that incompleteness does in terms of the halos that host those galaxies. But that basically means you already need to know what the galaxy halo connection is, and you can remove the halos that don't host the galaxies that are not in your sample. But that sort of requires that you know the answer before you get into it. So you basically need a complete sample, is the answer.
It is a little bit of a naive question, but with the CMB having such constraints on cosmology, right? Obviously, you want to confirm those results with other probes.
Right.
But does it run into some problems that are also connected to what we've seen here, or is it completely independent of like galaxy center bias?
What? So I don't understand the question. Sorry.
The constraints with the CMB, right, are already pretty good.
Yes.
Right? So I guess my question is, with so many problems like this, right? And are there any equivalent problems like this? Obviously not the same, but with the CMB block.
Oh, you mean other? Should we? I'm not sure I understand the question.
What are systematics in CMB?
What are systematics in CMB data? Oh, I'm not a CMB expert, but as far as my understanding is that if they plot particular confidence intervals on cosmological parameters, they claim they've taken everything into account. I don't think there's serious uncertainties there. The physics is fairly simple. Okay, at that time, that's a nice thing. It's not galaxy formation, non-linear stuff. It's all linear regime, simple stuff. Are there any any uncertainties there? I don't think so. Maybe maybe if you do some weird cosmology stuff, there's some, but it's typically people assume, do this within a fixed framework of cosmology, right? Like the vanilla cosmology with 6 parameters.
If the belief is that there aren't any strong systematics that are there, strong
Okay. That's a good question. Right? So as I said, this is done within a particular framework, the analysis. Typically, we have a 6 model lambda CDM, and that seems to fit everything. Everything except maybe this stuff here at low redshift. And if this is a problem we can't solve, then maybe that's an indication that we need to go beyond this 6 model vanilla lambda CM model. We need to add some bells and whistles to our cosmology that still fit Planck, but it can also fit the low redshift data. Right? So non-zero neutrino mass might be one, or there's all sorts of weird ideas out there. So that's the idea. Right? So the hope is that with low redshift data, we can find a discrepancy that can tell us something about new physics.
Let's one more quick question, maybe, and then let's take a break.
Thanks, Frank, for the really great lectures. I guess I had a question about what you think might be the actual solution to sigma 8 tension, because it seems like you really trust the Planck data, and you mentioned all these issues of assembly bias, but
I'm by now convinced it's something assembly bias. But whether we can, assembly bias is wickedly complicated, right? All these, it depends on everything, and so how to constrain this in a meaningful way, I don't know, but it looks like all the recent work seems to point in the direction that, okay, there is indeed sufficient freedom to basically solve the problem, or at least make the problem much less severe. So probably that's the answer. It's very annoying. I was hoping we could do some interesting cosmology, but yeah.
You can type up questions in the Slack channel, A_2_lectures, and lectures can answer them there, or anybody can. Let's take a 15-minute break and be back at 11:10.